This video goes through the circular motion derivations for the Leaving Cert Higher Level Physics course. You may be asked any one of them in your exam. There are 4 derivations in this chapter. Linear speed with angular velocity, v equals r omega. Centripetal acceleration, a equals r omega squared. Centripetal force, F equals mr omega squared, and Kepler's third law, which relates the periodic time t squared to the other variables there. So the first expression we're asked to derive is the relationship between linear speed and angular velocity, v equals r omega. As with all your derivations, you'll need to memorize your starting point. And for this, we're going to start with linear speed. Okay, just regular speed. And by definition, speed or velocity equals distance over time, or s for displacement over t for time. V equals s over t, and that's by definition. Okay, so now we need to relate linear speed to angular velocity and to motion in a circular path. And if we look over at the diagram on the right here and recall from the video on circular motion that the angle theta swept out can be related to the radius of the circular path and the linear distance around the arc of the circle S. Okay, and we saw that theta could be given by S over R. And when S and R are equal, we got an angle of 1 radian. So taking this little equation here, let's manipulate it, multiply both sides by R, and you can get an expression for S. S equals R theta. Alright, what we're going to do now is we're going to substitute S in our first equation at the top there. So now we will have V equals, instead of S we're going to write R theta, and that should be divided by T. Alright, and since we know what theta over T is, it's the angular velocity. So what angle is mapped out or swept out per second? We have, this is where omega comes in. That's the angular velocity equals theta over T. Then we can say that V is equal to R omega, and that's our derivation finished. So look back, what's the starting point? What variables do you need to introduce, and how do you arrive at the end point? Practice that on a blank sheet and you can gain definite marks from that. Next we have centripetal acceleration, a equals r omega squared, to derive. Okay, and our starting point for that is a formula. You find it in your formula books. And it's going to be a equals v squared over r, where v squared is the linear speed. Okay, now you don't have to derive that one, that particular one. You just need to have it to hand as your starting point. So we're just going to make a series of substitutions. From the first derivation on this video, we've learned that v is equal to r omega. Okay, and we're going to substitute for v in the equation above, and now we're going to have a equals r omega squared on the top line divided by r. Okay, we'll get a equals r squared omega squared over r, and of course now we're at a place where we can divide by r, and we'll get a equals r omega squared, and there we are at our finish point where we want it to be. That's your second derivation. Your third derivation is for centripetal force, and this one actually is quite straightforward. We're going to start with Newton's second law. So that's your starting point. So I'll just say Newton's second, which is of course F equals ma. And from the previous derivation, since A is equal to R omega squared, we can simply substitute for A in F equals ma, and we can say that F equals m R omega squared, and that's job done. The fourth and final derivation in this chapter is for Kepler's third law, which you see here. So where to begin? What is your starting point? So for this one, your starting point is to equate, put equal to each other, the centripetal force should be equal to the gravitational force. So this is for orbiting objects. Okay, so using the formulas we have for centripetal force we saw in the previous derivation is m or omega squared, and the gravitational force from Newton's law of gravitation, g m, where they're the two masses, over r squared. Okay, now we can manipulate this a little bit. Okay, I'm going to divide both sides by m and r. Okay, so that I get omega squared equals. So I get omega squared equals, dividing both sides by m, they disappear, that's the mass of the smaller orbiting object, and dividing by r gives me an extra factor of r on the right hand side. I get r cubed where there was r squared before, and we still have the gravitational constant g and m, the mass of the larger object there. Okay, now we need to introduce t, the periodic time, and that was given by t equals, so a full revolution 2 pi divided by the angular velocity. So how long did it take the orbiting object to complete a full revolution? Okay. Alright, and just manipulating that a little bit so that we get omega equals, 2 pi over t. Is that okay? And now we have an expression for omega, which we can substitute into this equation here I'm marking on the left. Okay, so we had omega squared, so now let me put in brackets. Instead of omega squared, I'm going to have 2 pi over t to be squared, should be equal to g m over r cubed. Okay, so we're going to have 4 pi squared over t squared is equal to g m over r cubed. And the next step will then be to invert that. So when you have one fraction on either side, you can invert both, and that will give us t squared on the top line, because we want our expression to be t squared equals. Okay, so inverting, we get t squared over 4 pi squared equal to r cubed over gm. So you're turning both sides upside down, and now to arrive at t squared, we will multiply both sides by the 4 pi squared, and what we'll arrive at then is t squared equals 4 pi squared r cubed over gm. So that's pretty much it. Okay, now where does the r plus h come into it? Well, in this expression we've just got that I've put a rectangle around, r cubed refers to the radius cubed, where the radius is the radius of orbit. Okay, now if you had a satellite orbiting a planet, let's take the planet Earth, then the total radius of orbit would be the radius of the Earth plus the height above the surface. Okay, so we're just going to replace that r cubed in the previous expression. It was 4 pi, so you would take r to be the radius of the planet or the whatever's been orbited, plus h, the height above the surface of the satellite, will give you the total radius of the circular orbit rather, over gm. And there we have Kepler's third law.